Hello, welcome back. Okay, now in this video, we will discuss continuous random variables and the associated probability density function of a continuous random variable. A random variable x is said to be continuous if it can take all possible values in an interval of real lines. Sometimes it may be the entire real line or it may be a subset of the real line. And associated to a continuous random variable, we can have a probability density function. And in probability density function, it doesn't mean the probability at a particular value as in the case of a discrete random variable, but it is concerned with the probability of an interval, in particular a small interval uh, of the real line at a very small neighborhood of x. And we may consider the small interval x to x plus dx of length dx from x to x plus dx, where dx is a positive quantity but it is very small usually. And let f of x dx represent the probability that x falls in the small interval, or it is technically called the infinitesimal interval x to x plus dx, where f of x is a continuous function of x. And f of x dx is the probability that x falls in the interval x to x plus dx. So that f of x is equal to a probability that x takes value in the interval x to x plus dx divided by the length of the interval. Usually when this dx is very small. Or in other words, using the notation of limit, f of x is the ratio of this probability to the length of the interval. As the length of the interval dx becomes closer and closer to 0, or it becomes very, very smaller. Then this function f of x is called the probability density function of x. Okay, and this density can also be defined as similar to the earlier definition, but it is concerned with the interval from x minus dx by 2 to x plus dx by 2. And however, the length of the interval is dx in this case also, and you take the limit of the ratio of this probability divided by length of the interval dx. Okay, and from the definition of f of x from calculus, it is known that the f of the probability that x lies in an interval a to b, that is equal to integral a to b f of x dx. Okay, and you can see here one point that in this expression, suppose you put b equal to a, that is probability that a less than or equal to x less than or equal to b. That means the probability that a less than or equal to x less than or equal to a itself. Okay, and the right hand side you put b equal to a, so that this right hand side becomes integral a to a fx dx. And from calculus you know that integral from a to a fx dx equal to 0. That is, right hand side becomes 0 when this b is equal to a. And what is the meaning? Probability that a less than or equal to x less than or equal to a means probability that x equal to a. And probability that x equal to a is nothing but 0 because of the result in calculus. Okay, that means probability that x takes a particular value a has 0. it is true always for all real numbers probability that x takes a particular real number that is equal to 0. So for continuous random variable, probability is not defined at a particular value. Whatever be the value, probability that x takes a particular value is equal to 0 because of this concept. Okay. And further, probability density function f of x has two conditions. The first condition is that f of x is greater than or equal to 0 for all x. That is, the density function is always non-negative for any real number x. And similarly, the integral over the entire real line fx dx, that is equal to 1. And this, in fact, the total probability that is equal to 1. Okay. And of course, this is a necessary and a sufficient condition for a continuous function f of x to be a PDF. That means if f of x is a PDF, these two conditions are satisfied. And if any continuous function f of x satisfies these two conditions, then that is a probability density function of a continuous random variable. Okay, so for checking whether a continuous function is a PDF, you can verify these two conditions, right? And you can see, as I have already told you, f of probability that x takes the value small x that is equal to 0 for any real number, that I have already argued. Okay, so consequently all these probabilities are same, and all these probabilities are nothing but f of f of b minus f of a, where a is the lower limit and b is the upper limit of this interval. So whether this b is included or excluded. Similarly, whether a is included or excluded, all these probabilities are same, which is equal to fxb minus fxa, where f of x is the probability, the cumulative distribution function of a continuous random variable. Okay, and we can see some result that you have an alternative definition of a random variable like this. A random variable x is continuous if capital F of x is continuous, and a random variable is x is discrete if the distribution function is a step function of x. We have seen what is meant by a step function in the earlier definition. In the earlier lecture, we have considered a step function, and we were considering step function when we discussed the discrete random variable. Okay, and you can have some examples of a distribution function, and you can identify whether the x is a step function or a jump function. Okay, if it is a jump function, then you can see that there is a discontinuity at that jump point. Okay, and you see what type of distribution is this of the random variable x. You can see that this distribution function is the distribution function of a discrete random variable. Why? For that purpose, you can verify capital F of x at x equal to some particular value. Now you see, you can see that f of 0 minus, this is actually f of 0, this minus means a value just below 0, not 0 but just below 0. And you can see that this f of x is given in terms of a formula for various ranges. So while calculating f of 0 minus, you have to use this range minus infinity to 0, because it is just below 0. f of x equal to 0. So if you put 0 at f, that becomes 0. And what is f of 0 exactly? You see, this f of 0 and this f of 0 are different. This f of 0, the right hand side f of 0 is the distribution function value at 0. But this f of 0 is the distribution value of a real number just below 0. So when you compute just below 0, you have to use the first formula, that is 0. Okay, and when you take the exact value 0, you have to use the second formula, because this second formula is for all x including 0. And you can see that f of 0 minus 0 and f of 0 both are same, equal to 0. And what about f of 1 minus? When you compute f of 1 minus, you can use the formula here, second range. You put x equal to 1 at the second formula, you have a 1 by 4, 1 by 4. And f of 1 you have to use the third range. So you put x equal to 1 in this formula, 2x minus 1 by 4. So when you put it is equal to 1, you see that minus 1 square by 4 plus 3 into 1 by 2 minus 5 by 4. You can compute, it is equal to this 1 by 4. So f of 1 minus as well as f of 1 both are 1 by 4. Right. And again you compute f of 2 minus and f of 2. When you compute f of 2 minus, you use the third range. So you compute the third formula, fourth formula. The third formula. So you see that f of 2 minus is equal to f of 2, both are 3 by 4. And similarly, f of 3 minus and f of 3 both are 1. Okay, so there is no difference between f of 3 minus and f of 3. Similarly, there is no difference between f of 2 minus and f of 2. And this means that the distribution is a continuous distribution, or the corresponding random variable is a continuous random variable. So for checking whether a distribution function is that of a continuous random variable, you can use the technique of computing these the end values of different ranges. But you will see that this is not the case in the next example. In the next example, you can compute f of 0 minus, that is equal to 0, but f of 0 is equal to 1 by 2. So f of 0 minus is not equal to f of 0. Okay, so that means what? At 0, the distribution is not continuous. It is not continuous. And what happens? How do you compute f of 0 minus? F of 0 minus can be computed using the range x less than 0 and f of x equal to 0 for that purpose. But when at x equal to 0, you have to utilize this formula x plus 1 by 2. So you put x equal to 0, you will get f of 0, that is equal to 1 by 2. Right? So these f of 0 minus 1, f of 0 minus and f of 0 are different. So at x equal to 0, there is a jump. Okay. But one point here you have to check that in between 0 and 1, for various values of x, this x plus 1 by 2 varies, and you can see in this range throughout it is continuous. That means it is not a step function. And when x equal to 1 or more, you have f of x equal to 1. f of x equal to 1. Okay, and this thing will be clear if you draw the graph of the distribution function f of x. Okay, and you can see this graph, right? At this graph, what happens? At 0, up to 0, f of x equal to 0. But at x, it has a jump to 1 by 2. But after 0, in the range 0 to 1, the graph of f of x is steep and continuous up to 1, and after 1 it is always 0. Okay, so between 0 and infinity the distribution function is continuous, but at x equal to 0 it is not continuous. Okay, therefore the corresponding distribution is not a continuous distribution and not a discrete distribution. Why not discrete? If it is discrete, you should have a step function, but here it is not a step function. And what kind of random variable is this? It is neither continuous nor discrete. Such a distribution is called a mixture of distributions. Mixture of a random mixture of the corresponding random variable is the mixture of a continuous random variable and discrete random variable. So you can see that there are distributions which are not continuous and which is not discrete, which is not continuous. Okay, that is why we speak of a mixture of random variable or mixture of distribution. And similarly, you can have same situation in the third example also. In the third example, what happens? By seeing the distribution function itself, you can identify that at x equal to minus 1, at x equal to minus 1, what is f of x? You substitute x equal to minus 1, so that it is minus 1 plus 2, that is 1 by 4. Okay, so at x equal to minus 1, the probability is 1 by 4. And what is the value of f of x at x equal to minus 1 minus something, minus some epsilon? It is equal to 0. That means at x, it has a jump. Up to minus 1, f of x is 0. But at x equal to minus 1, probability is 1 by 4. Okay? And what happens at x equal to 1? At x equal to 1, what happens? Here, you see, at x equal to 1, the probability is, yes, x equal to 1, the probability is, the f of x is 1. But what happens f of f of 1 minus is this 1 plus 2, 3 by 4. So probabilities are different. Okay, that means here there are two discontinuity points. One at minus 1 and the other at 1. Okay, and in between minus infinity to 1 it is 0, continuous, but at x equal to minus 1 there is a discontinuity, it undergoes a jump. Okay, and from minus 1 to 1 it is constant, it is not constant, it is continuous and increasing, but at 1 it again undergoes a jump. So the corresponding distribution function has two discontinuity points, one at x equal to minus 1 and the other at x equal to 1. And if you draw the graph of this distribution function, you can see that at minus 1 there is a jump and at 1 there is a jump. However, this is not a step function. Okay, therefore, this distribution function is also a distribution function of a mixture of distributions. You can have many examples of mixture of distributions. Okay, and we see that there are two types of random variables, one discrete, the other continuous, and the third one is the mixture of random variables. And in this example, you can compute the probabilities. You can compute the probability between minus 1 by 2 and 1 by 2. Okay, that is equal to f of 1 by 2 minus f of minus 1 by 2. You can compute it is equal to 5 by 8 minus 3 by 8, which is equal to 1 by 4, using the above technique. Similarly, you can compute all these probabilities. Probability at x equal to 0, that is f of x, f of 0 minus f of 0 minus, it is equal to 0. Similarly, probability at x equal to 1, that is f of 1 minus f of 1 minus, which is equal to 1 by 4. And probability at x equal to minus 1, it is nothing but f of minus 1 minus f of minus 1 minus, that is equal to 1 by 4 minus 0, that is equal to 1 by 4. What do you mean by f of capital F of say x minus means, or if you compute the probability at a particular value, if you know that it is a purely continuous random variable, then you know that f of x equal to minus 1 is 0. But here f of x equal to minus 1 is not 0, but it is equal to 1 by 4. Similarly, probability at x equal to 1 is also not 0, it is equal to 1 by 4. Okay, but at x equal to 0, it is equal to 0. It is equal to 0. Okay, however, you can see in the above discussion that three types of random variables are there. Okay. Now, these are the things regarding continuous random variable and mixture of random variables. Okay, thank you.